All right, so let's take a look today at valence electrons, and the goal will be to differentiate between valence electrons and core electrons. The reason why we talk about valence electrons is that they're important for determining the reactivity of an element on the periodic table. And whenever we look at our valence electrons, whenever we draw orbital diagrams or we write electron configurations, it can help us to determine the number of valence electrons and essentially confirm what we've talked about with valence electrons so far. So valence electrons are electrons in the outermost principal shell or the principal energy level. And so this is going to have the highest principal energy number or the highest principal quantum number. The core electrons are not in the outermost principal shell, so they would be closer to the nucleus than those valence electrons. This should give you an idea. If we're looking at an electron configuration, we have the core electrons and then the valence electrons. So the valence electrons are principal energy level number 3. When this gets tricky, or when this is maybe not, the valence electrons might not be the last number that's written, is whenever we have a D subshell or an F subshell present. And so in this case, whenever we look at our valence electrons, they are the S subshell and the P subshell for principal energy level number 4. And the core electrons are all of the lower principal energy levels. So even though 3D10, so 3D has higher energy than 4s, 4s is still further away from the nucleus, making it the valence electrons. The valence electrons will always come from the S and P subshells. So here's an example. If we have magnesium, which is going to be 1s2, and then 2s2, 2p6, 3s2. I don't know where the 2 went for that. So this would be 3s2. So our valence electrons in this case are going to be these 3s2, and so we have 2 valence. The rest of these ones would be our core. If we look at nickel, then nickel has 4s2 and then 3d8. So these 3d and then everything leading up to 3p, these would be the core, because again, even though it's higher energy, it's still closer to the nucleus, and then we would have 2 valence electrons. Here's another example. If we look at silver, silver is an exception for its electron configuration, so it actually is going to be 5s1, 4d10. We talked about these exceptions before, but this means that silver has 1 valence electron. Strontium is going to form an atom that has 2 valence electrons. The valence electrons correspond with what we talked about in the past with the periodic table, where family number 1 has 1 valence, family number 2 has 2 valence, and then we have the boron family, the carbon family, and the valence electrons increase as you go across the periodic table. This middle section is blank, and this is because the number of the outer shell electrons in a transition series or in these transition metals don't necessarily change. So as you go through these transition metals, they still have whatever level S2 here, and these ones would really be the ones that are going to be the valence electrons, whereas these D subshell electrons are going to be in the core group. So let's go ahead and take some time to practice. So how many valence electrons are in each of the following atoms? You can go ahead and pause this video and then check your answers. All right, so our answers here, we have S and P for our valence electrons, so we would have 8 valence electrons. For the second example, we have 4s2 and 4p4, those will be our valence electrons, and so we'll add those together for 6 electrons. We'll do the same thing here. We'll take our principal energy level number 5. And so we have 2 and 2, so this would be 4 electrons. And then in this last example, we have 3s2, 3p3, so we would have 5 valence electrons. Go ahead and do a little bit more practice. So why don't you go ahead and write the electron configurations for the following and then determine how many valence electrons they have. You can go ahead and pause the video and then check your answers. So our valence electrons are as shown, Helium has S2, so that'll be 2 valence. Whenever we look at oxygen, 2s2, 2p4, that would be 6 valence. For sodium, 3s1, so that's 1 valence. And then for chlorine, 3s2 and 3p5, so that is going to be 7 valence electrons. Whenever we look at valence electrons, it helps us to explain why certain elements are very reactive and others are not. And as we look at ion formation, we'll see how these elements strive to be closer to the configuration of a noble gas by losing or gaining valence electrons.